Hello, hi. Did everyone join? Am I audible? Call. Session we have discussed and also design part discussed. Okay. System Verilog verification need to discuss for I2C protocol. So did you remember the till design part? How to write the program using finite state mission? Can you tell me how many number of states are there in I2C? How many number of states? Aditi, Vinita, what about Ramani? What is the difference between clock stretching and arbitration concept? Clock stretching and arbitration. Your voice is not audible.
Like cloth stitching is basically we use when slave is in work another work another task. So like we need to disable it to disable it to low so that it can work, and when its clock is high, then we can start the further work like that.
Okay, how can we write clock stretching in design code? Coding wise, how can we write the clock stretching?
Like clock stitching using if else condition. Like when clock stage is high, we select the clock line to 0, and if it's low, then we select the serial clock line.
Okay, okay, fine. What is mean by arbitration concept?
Arbitration concept.
Others? Any answers from others? Arbitration, clock stretching in the sense whenever both master and slave are working at different frequencies to make the synchronization between each other, we make as a constant clock as a constantly low, so that it is waiting until the functionality should be completed. Whatever the current transfer is there, it is waiting to complete the current transfer. That's what we are telling as a clock stretching, right? In I2C protocol, we have this frame format. You already know how the frame format is working, and we already designed the finite state mission. So if you see here, SDA and SCL are the two signals in I2C protocol. So we have a start condition and also stop condition, right? So start condition is nothing but whenever SDA must be high to low and SCL must be constantly high. Stop condition is nothing but whenever SDA is low to high and SCL must be constantly high. Start or stop. So here we are using address and data. So first we need to select the address, slave address. So if there are multiple number of masters, then which master need to initiate the transfer? That concept we are using through arbitration. Arbitration concept we are using for selecting the master. We already discussed very clearly on arbitration concept and clock stretching concept, right? So by selecting any one of the master, we are passing the address to the slave, so that we are selecting any one of the slave. Okay, and after that, whether it's a read operation or write operation, after sending the address, there is a signal called R by W. Based on R by W signal, here we are selecting either read or write. And also acknowledgement signal. Acknowledgement signal is nothing but we will get the output whether the received data is correct or wrong. Whatever address or data, whether it is correct or wrong, based on the acknowledgement signal, we will get to know, right? And after selecting the address, we need to store the data into the particular address. So then data line will be started. So D7 to D0. Okay, if data is sent correctly and the slave is received properly, then we will get the acknowledgement signal as successful, or else we get the not acknowledgement signal. Okay, so it means the data is not successfully sent. So this is what I2C frame format. We have seen all the different signals and also finite state mission, and also we have seen the multi-master support and clock stretching concept. And also we have written the finite state mission and also program. Just theory wise completed. What are the steps we have in finite state mission? Ideal state, start, register address, register acknowledgement, write data acknowledgement, read data acknowledgement, stop wait to stop. So clock stretching concept is nothing but, if you see here the definition, master operated high frequencies, slave will operate at low frequencies. There are some situations where I2C master will not able to cooperate with the clock speed. So whenever there is a mismatch between the clock frequencies at master side and slave side, one is working very fast, one is working very slow. So to make the synchronization between each other, whatever the frequency is working fast, suppose master is working fast or slave is working fast, we are making it like just making it as a constant value. Okay, so slow down, just making as a slow down. That concept we are calling as a clock stretching. So how to write the program in the sense, SCL is equal to, whenever the clock stretch is high, output is assigning to 0. That is what the condition, right? So assigning to 0, or else SCL must be assigned to SCL. Next, arbitration concept, you already know, in which case master will won, any one of the master will won the bus and will lose the bus. Okay, so now today we will discuss the system verilog program, and in the next session, Saturday session, we are going to start with the APB protocol specification we will discuss, and then system verilog verification. And next will be AHB total specification, bus transfers, and remaining all type of transactions, and also detailed RTL design and UVM verification for AHB, AXI, all entire specification AXI4, and also we are discussing on different features and how to write the test plan and how to write the VIP development for AXI protocol. Okay, so this is what our plan. Actually, before sessions in Saturday, Sunday, we have discussed in morning sessions, right? Morning at 11 o'clock to 1 o'clock. But from tomorrow onwards, I mean next Saturday onwards, we'll have a session at 7 o'clock. So morning, I have another sessions with IIT Delhi. So evening, we'll have these protocol sessions. Okay. Uh, First, coming to the Verilog design program, already completed. We already discussed very clearly, and how can we connect these test bench slave.v. Okay, so module and name of the module, what are the input, output, and what are the internal, signals, wire signals, or temporary variables we can call, because we are declaring as a rich data type. And enable signals, control signals in the sense, because mostly we are writing different blocks in your protocol we have seen, right? So suppose if there is a mux, so selection line is a control signal. If there is a counter logic, counter enable is a selection line. If there is a serial in parallel out, shift register, so we need to convert the serial data to parallel data. For that also we must have serial in parallel out enable signal, or parallel in serial out enable signal. So whether the data is correct or not, to check that we must have some valid signals. Okay. So in the same way, in I2C also we have write enable, read enable, read start, stop, and count enable, serial in parallel out enable, parallel in serial out or enable, serial in parallel out, valid signal, stop enable, parallel in serial out valid, and start enable. Whenever the start enable is high, it will detect the start signal. Whenever stop enable is high, it will try to stop the transaction. At the same time, it must have the condition, whatever the condition we have writing, SDA must be low to high and SCL must be constantly high. It should be reached that condition. Okay. So next, we have finite state missions, ideal state, start, register address, register acknowledgement, write acknowledgement, read acknowledgement, stop and stop wait. So based on that, we already written the FSM, right? I think I no need to explain again. If you have any doubts, you can ask now. We will discuss. And if you want to have some revision, already shared the recorded sessions, right? Just go through the recorded sessions. Okay. So these signals are just for directional enable, whether one direction or bidirectional, and the temporary variable data output data is assigning to the main data, and address in whatever the input address we are generating, it's a 8-bit size or 7-bit size. In that we are assigning to the address out, comma, write read operation, and remaining all code is the same. Just go through that. Is there any doubts in the design program? Anyone? Hello,
No, ma'am.
Sai.
So the code where you write the concept for when two master is tries to get a single slave, and ma'am the clock bit when we elongate the clock, the two concept in RTL.
Clock stretching and multi-master arbitration you are asking, right?
Yes, ma'am. Yes, ma'am.
Actually, clock stretching we have written here. That's what I have shown now. But multiple master we haven't written. Multiple master in the sense, here in this example we are considering slave as a test bench, master as a sorry, slave as a design, master as a test bench. Okay, so master considered as one master only, not design. If you want to go with a multiple master, master also we need to write as a design, same as a slave, and two masters you can write. However, we took like I2C slave dot v, like that you can take master one, master two, master one, master two also, same final state missions only we need to write. In that master 1 and master 2, we need to write the arbitration concept. So in the top level test bench, you need to connect master 1 and master 2. Based on the input transactions, you can select any one master. Okay, so in this program we didn't included two masters, but if you need, I will share that code also. I will check, and once I will share that multiple master also, or else even I will write some piece of code, and I will share to you afterwards. Okay. So coming to the clock stretching, here we have written stretching. So directional enable, assign SCL is equal to clock, and SDI is equal to directional enable signal. Clock stretch is equal to SCL. Okay, SCL directly assigned to here. Clock stretch is not used. Clock stretching is not written here. Both the examples here, master here slave is a design. SDA and SCL signal are taken directly, and here also directional enable and also main data out address in and here negative edge clock positive edge reset according to our condition. We must have negative edge here. SDA must be negative edge and SCL must be positive edge, and that too constant value. So same thing written here, but clock stretching is not written in this example. Sequence directed. I will share you the clock stretching and multiple master, both the codes. But clock stretching we need to write like this. SCL is equal to whenever clock stretch signal is high, it should go to 0 and SCL should get same value. So what is this clock? This clock is nothing but the main clock variable here. This clock signal, see, assign SCL is equal to CLK. Okay, so in place of CLK, you can take as a clock stretch. Okay, so whenever clock stretch is high, you need to assign like this. Whenever clock stretch is high, it should go to 0, making constant. Whenever clock stretch is 0, SCL must be sent to the SCL. Same clock. Okay, so this condition you need to write once. Try from your side also. Okay, so this is what the design code. Is it clear?
Uh, here for serial input parallel out, and the last part is not clear.
See,
For parallel and serial out, negative serial input.
why we are taking posage and negate? See, when in which case we use serial in parallel out and in which case we use parallel in serial out. Okay, so master to slave is a serial communication here. I2c protocol means master to slave, it's a serial communication. But whenever we are, suppose here there is a total SOC. In a SOC, every functional block will be communicated to each functional. Suppose processor is communicated to memory system is communicated to low peripheral devices. Okay, suppose if you consider it as a processor, okay, so the processor is communicating with a low power peripheral device. So how the processor will be communicated to low power peripheral device? Obviously the data will be coming like this. Already I have shown you SOC architecture also. So from the processor, the data is sending to the some small IP. So how the data will be sent from processor to here? through the interconnect. What type of interconnect will be there? We have high speed interconnects and low speed interconnects. High speed interconnects are nothing but AXI. So here AXI protocol is used. But coming to the low power peripheral side, AXI protocol will not work because that frequency is different, and here whatever the low peripheral devices are there, these frequencies are different. So for that purpose, we are using APB protocol here to transfer the processor data to low power device here. In middle, there will be a bridge connection. So AXI to APB bridge. Even though it is a APB, the data will be in a parallel communication only. To this master, the data is coming in parallel communication. Okay. But here there is a master, which is I2C, but this master will accept only serial data. Okay, so whatever the data is coming from this master, it will converting to the parallel data to serial data. Okay, so the serial data one by one bit is transmitting to slave here. The slave can send to the another master. It may be same master sometimes, or it may be some other devices it is communicating. Suppose this slave is communicating with some memory controller, suppose. Okay, but here memory controller will accept only parallel data because mostly we use APB protocol here. So to convert this serial data to parallel, we are using SIPO, serial to parallel converter. Okay, so from master side we are using parallel to serial communication, and slave side we are using serial to parallel communication. If you go to frame format and check, and there will be a start condition and there will be a stop condition. Start condition means what? High to low. SDA must be high to low. SCL must be constantly high. It's a positive, negative edge. See, low to high to low means negative edge trigger, right? But stop case, low to high. Low to high means what? A positive, positive edge trigger. And also SDA must be low to high. SCL must be constant, that to positive edge trigger. Okay, so that's why we have written here, even if you see at starting, for start condition and stop condition here, always at the rate of negage SDA. Negage SDA means here high to low for start condition. SCL must be constantly high here. Okay, so SCL is negate, SCL is constantly high, SDA is negate. Same way, in stop condition, SDA is positive edge and SCL is constantly high. Okay, same conditions written in parallel in serial out case also. Serial in parallel out. Serial in parallel out means where we used slave side. Okay, so what is the stop condition here? Serial in parallel passage SCL. If you see here, passage SCL. So that's why here we have written as a passage SCL with respect to. And parallel in serial out, where do we have parallel in serial out? Near master side. And master side, what is the condition? Start condition. What is the case for SCL? High to low. High to low means negate. So for piezo, negate SCL. Did you understood now?
Yes, understood.
And also internal conditions, you know how to write, how to convert the parallel data to serial and serial data to parallel. Okay, so everyone once go through the design program once again. So same master and slave here, however we written, uh, design is entire finite state mission, and master is a simple test bench here. Now we'll see how to write system Verilog test bench. Okay, so can anyone tell what is the difference between interface and virtual interface from protocols batch? Interface and virtual interface. No idea?
Interface is used to communicate between DUT and the driver, And virtual interface is used as instead of interface as a uh, what to say. I'm actually forgetting that.
Talk with like static DOV and dynamic test bench.
Okay. So interface is like just interconnecting the test bench and the design. Okay, so normally whatever the interface we use, it's a physical interface which is a static in nature. But in system Verilog, we use everything in a class-based verification using object-oriented programming like that, right? So that's why we can't use normal interface which is a static in nature. For that purpose, we are creating one virtual interface which is a dynamic in nature, okay, which can be communicated easily with the classes and objects. Okay, so we already discussed how to create the interface and how to create the virtual interface. Just we need to create the normal interface, physical interface. To that, if you add a virtual, it just work as a virtual interface. Okay, so here see, whenever you are writing some system verilog program, okay, for practicing or any design, whatever the design you have considered, whether it's a small adder example or any register example, whatever the FSM memory, whatever, first start with the interface block. Okay, after interface, then write transaction class. Okay, so first how to write the interface name of the interface, input, logic, clock, comma, reset, and all input and output variables must be declared here. Okay, so can you tell me why do we declare as a logic data type here? Why don't we use reg and wire data type? What is the use of logic data type in system verilog?
It can be used for both wire and reg.
Mm, okay. Is confused, and also
So
most of the cases we will get the simulation errors because of reg and wire. Always we need to check for input and output. So without having the problem in system verilog, we have as a logic data type, right? And next, what is the difference between clocking block and mod port? Block and mod port.
Outputs are used to direction the signals as per the uh, for example, for design, we need some signals as input and some signals as output. We can direct the signals as of our requirement in mod ports and use that mod port name in the code.
Okay. All inputs, it will work as a outputs to the driver. All outputs will work as a inputs to the driver, right? And for monitor block, whatever the signal is getting from the DUT, all signals will be inputs only, whether it's a input or output, whatever we have declared. But for the monitor, all the signals will be inputs only. That is how we write the clocking block. Mod port is nothing but just like a port list declaration. Okay. Clocking driver CB at the rate of negative clock. Default input 0, output 0. It is just a skew, hash 0 and output 0. Uh, and in out, you can mention as a in out and also or else input output. Okay. So SDA in out, address out, data out, and in the monitor block, all the variables must be declared as a inputs. So SDA, address out, data out are the inputs. Mod port driver, writing the mod port port list here. and also mode port monitor. For the monitor, we are writing the port list. Okay. So next,
In clocking block, we cannot use logic instead of input,
no,
or
it's not logic. It just input output port we need to mention, not data type, just data type declaration. Here, just a data type
okay,
declaration.
okay, yeah, okay.
In clock, we are making a directions, actual ports. Okay, so next transaction class. Transaction class in the sense whatever the data we are randomizing
In
and sending
in
to
the
the
clocking
DUT.
block, how are we assigning the direction? Like how is address out and input?
Here we are mentioning the direction, right? Actually, suppose if you take the driver and DUT, suppose it's a driver and DUT and the monitor, whatever the generator is randomizing, suppose A, B or the inputs, C is the output, right? So generator is sending A, B randomized inputs to the driver. So this driver is sending the data to the DUT. What data the driver is sending to the DUT? Nothing but A, B. So if you observe here properly, A and B are coming out from the driver. Okay. So A and B are the output signals to the driver, and actual outputs will be the input signals to the driver. Okay. But if you see here from DUT, whatever the functionality after completing the functionality, A, B, and also C, whatever the outputs are, all the data sending to the monitor, because monitor will fetch all the input from the DUT and it will be sending to the scoreboard, right? So here A, B, C are the inputs to the monitor. Okay. So that is how we write the port list here. Monitor, for monitor, all variables must be declared as inputs. In driver, inputs are declared as outputs, outputs are declared as inputs. Here,
And this clocking is a keyword. Uh,
yes.
So like before monitor you need to write this clocking like it's a normal syntax only.
We need to follow. And even pass positive edge also, that's not a problem. It totally depends on your spec. Here, negative edge clock we are using in the sense sometimes in the design we are passing the negative clock, right? For SCL.
So which clock
The-
is this?
Which clock?
Hmm. It's not SCL, right?
It's not SCL. To SCL we have added actual clock. Here SCL is there. To the SCL we have assigned actual clock.
So is it like the processor
Here
clock?
CLK. Processor clock. What is meant by processor clock?
When we
This is normal clock. However, we use in normal sequential logic circuit, we use some clock, right? So it's normal clock will be assigned to SCL. So whether it's a positive edge or negative edge based on the SCL, we are using. But actual clock is CLK. CLK is assigned to the SCL. As per our requirement, we need to change the SCL condition.
S clock, SCL as a clock. We have to assign.
Directly SCL, how we can mention, because SCL is related to the design part. So normally we are generating some clock and assigning to the SCL. Based on the requirement, we are changing the SCL. The actual clock will be same. See here in the test bench, here in the test bench, we are generating the actual clock. Whatever the feature of the clock is there, like on off, that will be same. Okay, based on this clock value, we are assigning to the SCL. If any requirement is there according to the SCL is negative edge changing or positive edge changing, based on that we need to write in the design. We need to create the actual clock first. Even if you see in UART protocol, we create some clock. Based on the baud rate, we will change the frequency.
Okay, yeah, got it. So SCL is the design part actually.
Design
So,
part.
okay, okay.
Yes. Next, coming to the transaction class, input or declared and output inputs must be declared with a rand or ranc. What is the difference between rand and ranc? Ranc, tell.
In the cyclic.
Yeah, ma'am, in rand, say it uses also the random value. Once the one cycle means all the value is used, then it repeats. Otherwise, means it's a cyclic. Means all the value got multiple times. Uh,
Okay, rotate in a cycle. Till then, it won't generate any uh, same values. Same value. That is what rand say. But in interface, we cannot write the rand. In transaction, we need to write the rand. Why? Because in the generator, we variable, you can write randomizing the transaction data. In the transaction, we are mentioning all the data. In Verilog HDL, if you want to randomize a variable, you can randomize only one time. If there are 100 variables, 100 number of times you need to use $random. A equal to $random, B equal to $random, C equal to $random, D equal to $random, E equal to $random. Like that, whatever the number of variables is there, every variable we need to assign. But in system Verilog, because of object-oriented programming, we are creating the object for the transaction class. Suppose transaction is the name of the class here. We create a object tr. By using tr dot whatever, we are accessing all the variables by using a single condition, just tr dot randomize. So whenever you do tr dot randomize, whatever the input variables are there within the transaction class, all the variables will do the randomization. Okay, even 100 variables also will do the randomization. That purpose only we are differentiating here. Inputs must be declared with a rand, outputs no need to declare as a rand. If you declare here output as a rand, output will also do the randomization. Okay, if you don't declare inputs as a rand here, inputs also won't do the randomization. Okay, to differentiate that thing, we are declaring the inputs as a rand here. Okay, in the generator we are doing the randomization. So the randomized method will work whenever inputs are declared with a rand only, rand or ranc. Otherwise, those variables will not be randomized. Okay, if there are 32 number of bits, 32-bit address, no need to use 32 number of combinations of the same particular address, right? So real time we can use, but practice wise or in even in real time also, no need to use all to power 32 number of addresses. Whatever the particular specification according to your specification, you can pick some value for data and also address. Okay, so for that purpose, to make the controllability on randomization, we use the constraints, and also here constraint C1 is equal to C1 of write address is equal to 8-bit data 00111010. So
One quick question, Prasanti, just on this topic, then on constraint. If we use a constraint called unique or something like that, then we can't use rand C, right? I mean, I was getting the compilation error that saying with unique we you can't use RD rand C. Is it like that? Is it some limitation on rand C?
Actually, rand c in the sense it will generate only particular within the loop. Okay, it doesn't repeat any value. Coming to the unique, whatever the suppose 0 to 10 you are repeating. So unique in the sense only one value will be repeated one time. Even if you take inside also maybe it may repeat two times same value. But unique means only one value will be written one time. So that's why the
Hmm.
RANC is not working there. Suppose
Yeah,
you
I was
are,
trying that, but
what
it
is the
was not.
difference between inside and a unique queue? Uh, inside means within the range, any value can
Hmm.
generate even multiple number of times also it will generate if you use
Hmm.
inside. But unique means only one value will be generated.
Um,
That too, if there are multiple number of array concept, if you consider, for one array, one value will be generated. That is what we call as a unique.
yeah, yeah. Yeah, I mean, yeah, my doubt is like with the constraint, this kind of constraint, RAND C was not working. Okay.
Hmm. Okay, fine. So next, RD address is equal to 0011 Next, write data 0011011100. Okay. So based on these constraints only, output will be generated. Okay. Next, function to display some statements, and function void checker, just a small checker. Address out is it double equal to write address of 7 down to 1, because 0 bit is a write or read operation. So if address out is equal to write address of 7 down to 1, and data out equal to write data, then design is passed or else design is failed. Okay, you can write in a scoreboard, or else we can write like this small checker. Okay, so next, after transaction class, we need to design a generator. Okay, so class generator rand transaction tr. Tr is created. So whatever the variable or any function or whatever you want to access from the transaction class, you can access through this object tr only. Okay. So mailbox, need to create the mailbox. What is the use of mailbox in system Verilog?
to, to communicate generator to driver.
To communicate between generator to driver, we use the mailbox, and also to communicate from monitor
Different
to.
components.
Okay.
Scope.
Okay, so here mailbox gen2 drive is created, and function new, it's a constructor. Constructor in the sense to allocate the memory uh, for class, we create the constructor. Okay, so this dot gen2 drive, you already know why do we use this dot gen2 drive. Next, ask write address integer I is equal to 0 tr dot randomize. So if you see here tr dot randomize, we everyone completed randomized topics, right? So you already know how to write the randomization and constraints. So tr dot randomize, tr object is created here for transaction class. After doing the randomization, whenever tr.randomize is used, it directly go to the transaction class and check what are the inputs and what are the outputs. Whatever the inputs are declared with the rand data type, all those inputs will be randomized. Okay. So here, but in Verilog, if you see, if you want to randomize 10 different variables, 10 number of times you need to write dollar random like that, right? But here we no need to write. And next, tr.sdi is equal to tr dot write address of I. Okay, that data is okay, passing the data through the write address. Okay, fine. Next, dollar display of sda signal. Okay, fine. gen2 drive dot put of tr. That means whatever the data we have randomized in the generator block, that data we are putting into the mailbox by using the put method concept. Okay, so you already know to send the data into the mailbox, to store the data into the mailbox we use put method. To get the data from the mailbox we use get method, right? So in the generator we are using put method. And coming to the driver block, so here first of all, what is meant by driver? Driver is nothing but getting the data from the generator. How the driver will get the data from the generator? By using the mailbox, by using the get method. Okay, so whatever we got the data, the transaction data from the generator, that data must be sent to the DUT, right? So how it will be sent to the DUT? Through the interface. Okay, but can we use directly interface? We can't use. For that purpose we are creating a virtual interface. Okay, so from the generator through the mailbox, sending the data to the driver, driver to DUT via interface. As we are not able to use the interface directly, we are creating the virtual interface. Through the virtual interface we are sending the data to the DUT. That's what the path. Okay, so whatever the data is available in the DUT, that data is also available in the interface, in the clocking block. We need to access these clocking block variables actually. So how we are accessing these clocking block variables? Through virtual interface. Okay, so that's why in driver we need to create the virtual interface. So if you see here, macro define, here we are writing the macro. If you don't want to write the macro here directly, whenever you are passing the data from transaction to DUT, you can write here internally also. Okay, but if you set like this, no need to write always this entire path. Directly you can put the macro name driv if. Okay, so what is the path here? i2c VIF. i2c VIF is the name of the virtual interface. Actual interface name is i2c int f. Okay, so for this, if you see third line, for this i2c int f, we need to create the virtual interface. How can we create virtual? Name of the interface and name of the virtual interface. Okay, and mailbox gen2 driv. Okay, transaction tr, passing transaction tr. Next, creating the object tr for transaction. Function new, constructor for system, for class driver, and reset task. We need to wait until reset is high. Active low reset. driv f sda equal to 1. Need to wait until reset goes to low. And start condition. At start state, at the rate of i2c VIF clock. See how we are accessing the clock which is available in the interface. We need to access through the virtual interface. Okay, so VIF dot CLK, and next VIF dot SDA equal to 0, and at the rate of POSIX i2c VIF dot clock and stop condition. And write address we are passing C here, 45 line, 44 line, creating the object transaction. After creating the object, through the get method we are getting the data from the mailbox. After getting the data from the mailbox, next step, negative edge of the clock, passing the transaction data tr.sda is equal to driv.if.sda. What is this driv.sda? Nothing but this path. This path we are setting there. Okay, so driv.sda passing here. Whatever the transaction data is randomized, the data is passing to the interconnect. Okay, next whatever address output is there, that output we are getting from the interface to again transaction data. Okay, so dollar display statements write address and get no acknowledgement data, and same as the write data also. Getting the creating the object transaction and get of tr, getting the data from the mailbox at the rate of negate clock SDA, passing the SDA data to the virtual interface, and dollar display at the rate of negate I2c VF driver clock, and writing the display statement. Same as a reader, writer, read data, read address. All these tasks we are calling from here. Start task, write address, write data, read address, read data. Okay, you need to practice. I will share the code. I already shared the code. Just you need to practice till here.
One quick doubt, Prasanti. It may be very basic doubt as well. And like in where every time we construct the class in whether it is generator, monitor, I mean anywhere, but in the transaction class or wherever we use the constraint, like in randomization session also, I observed that we don't construct the class there.
In
Like in the
transaction,
transaction dot sv also, we didn't construct here like with the function new. You got my point?
but because here we don't have any connections for transaction class. In generator, if you see here, we have the connections. A mailbox is a connection, and for driver, mailbox and virtual interface is a connection. For monitor, virtual interface and mailbox is a connection. Scoreboard, mailbox is a connection. For environment, for transaction, we don't have any connections, right? So no need to create the class.
I mean in general also, if you don't consider the test bench also, like for example we were going through the oops concept and all. There we were constructing the class, but like when we come to randomization and construct, I never saw that function new. So just so it was in my I mean mind from there, like we never construct class in those programs.
Okay. Okay. So here actually, that's what I'm telling. Here we need to take the arguments. Actually, we need to pass the arguments. We have a requirement of taking these variables inside the function. So for that purpose, we are creating the constructor here, at the same time creating the class to allocate the memory. But here in this transaction class, we no need to create, because we are not uh, allocating any data here within the class. We are just creating some, we are just declaring some variables and some display statement. That's it. No need to call the transaction class anywhere. But in generator, we need to run this generator class. In the environment, we need to generate the generator, gen driver, driv, monitor, MBON, scoreboard, and we are calling all these tasks of generator everywhere. But do we call any transaction class anywhere?
Mm, mm,
Or just we are creating tr as an object and getting the data from the transaction. That's it. Already the data is
mm,
available in the transaction. Directly we are randomizing the transaction and sending the data to the mailbox, but we are not calling anywhere. So no need to create the memory for transaction class.
mm, mm,
But those objects we need to call. See, gen.main, drive.main, monitor.main, all the functions and tasks we are calling here. But in main transaction class, we don't have any function or task. Within the transaction itself, we are calling. Even though we have,
mm,
see, function void check, directly just check the output this whether it is correct or wrong. This display statement we don't call from anywhere. Even if you call through the tr dot display statement, we are calling. Okay, so here no need to create the memory actually.
Okay.
So through the constructor we are using this. Cross check and let me know. Here they're
Okay.
creating. So if you see here 44th line, that is what creating. If you just declare in the sense fifth line, transaction TR, just declaration is different, creation is different. Without creating, how it will allocate the data without creating the memory. So you
So
need to create.
so we need to create again and again because
Every class we need to create.
no, I mean
Not
TR has been created once,
hmm.
right, with this new thing, and after that also I think we have used this.
In this task we have created one time, and in second task we are creating again. In every task we need to create its own object, because here we are using this tr.sda in this task, which is a write data. Every task are different, right?
So we can't use it as a common and I mean create.
Or is there just use like tr is equal to new top level globally you are creating, and remove all task near all task and check what will be the output. Just cross check yourself also. Okay, next monitor. That means getting the data from DUT via virtual interface and sending to the transaction data. Okay, so here just setting a path to the interface via virtual interface and class monitor. Virtual interface is created, mailbox also created, class constructor, and task main transaction is creating. Wait until reset is 0, active low. Whenever it is active low, then only the main operation will work. So repeat 8 negate of clock, transaction tr is equal to new address out. Address out, tr dot address out is getting from the this monif is the path which we set here. i2c dot vif dot monitor dot monitor cb is address out. Okay, so setting the path to the interface clocking block driver cb, and then we are accessing sda. Okay, so after that dollar display monitor and monitor to scoreboard dot put off tr, so putting the data into the mailbox. So where we can get the data in the scoreboard monitor, monitor to scoreboard. So here also same, putting the data into the mailbox. And coming to the scoreboard, it's a simple scoreboard. Here we are not writing any golden reference values, because already in the transaction class we have written a small checker here. You can write like this, a small checker, or else you can write in the scoreboard also. Okay, so class scoreboard, creating the mailbox and creating the memory, function new, and task main, creating the transaction class, and monitor to scoreboard dot get of tr, so getting the data from the monitor, and tr dot display, calling the display statement in the transaction class, tr dot randomize, tr dot check. From here we are calling all the task of the tr through the object, this display function and check function in the scoreboard. Okay, generator, driver, monitor, scoreboard. Now all these four individual blocks we need to connect top level environment.
And please show
So
again scoreboard.
hmm, which one?
Scoreboard.
Scoreboard. Okay, scoreboard actually we need to get the data from the monitor and need to compare. Comparison logic we need to write in the scoreboard. Just whatever actual value we got and expected value we need to compare and check the whether the test is pass or fail. Okay, so here what we are doing, just getting the data from the monitor and writing the display statement, whatever the transaction, the checker we used here, comparing address out, input address is equal to output address and input data equal to output data, like that. Here we are just calling the task in the scoreboard, tr.check. Okay,
Like here, what is the use of this memory? What is like we assign
actually in the
memory?
scoreboard we need to create the memory because we are writing these comparison logics, right? For that purpose we create the memory in the scoreboard. uh, Most of the cases we create the queue for writing the comparison logic. Here we have created some memory.
So like we are not using also na in the task, right? This memory we are creating in the scoreboard, but in the code we are not using that.
In the code we are not using, because here when we call from, wait, let me show. In the environment, whenever we call from scoreboard, the function new bit, here we didn't return for checker. Actually, if we write for checker logic in the scoreboard, we need to use this memory allocation. But if you want to remove and check, you can check once. In this scoreboard also, I memo 5 is equal to 32 bit down 00. Mm, even here also created some memory, local RAM, local data. Here comparison logic has written here. So for that purpose, created the memory for local data. If you see local RAM of P address, so for this purpose, we have created the data and for local RAM and data created some memory. In the same way, however, we use the comparison logic here. We use same in transaction.
Mm.
Hmm? What?
That
In transaction class
so,
here we didn't use the memory, but we need to use the memory also here. Whatever the memory created, and in the transaction class, address out, write address, write data, data out, we need to create the memory. Or else directly we can create like this. Both are same. Scoreboard only we need to create, not in the transaction class. Actually, in scoreboard only we need to write the checker logic. But in transaction class we have written here. Mm, data out 11101101 reset SCL 221 hexadecimal DD. Okay, what are the inputs we have applied here? Input the address 67 DD. Here address 67 1100 110. 110 means this last zero will be the right. So 1106 0111 is a 767 address and data DD. So 67 address data DD is correct only. Okay, fine. So yeah, here that's what we need to create the memory in the scoreboard to write the checker actually. So here in transaction class we have written the checker, and even if you do the comment also no problem. Here direct memory is not using here, so same output you will be getting if you run and check. Same output is getting. 67 address DD is input data. So next after scoreboard environment, from the environment we will call all whatever function task or there in the environment we call it's a top level. For environment top level is a test. So in the test we need to call the environment. Test and interface will be called in the top level test bench. This is what top level test bench always set the rate of #5 clock initial begin. Interface 20 line 21st line. Interface and test both are calling, and assign SGA it's a directional enable and a DUT signal. So slave test and .p file. Okay, clear everyone? Just I will share the code. I already shared the code. Everyone try to connect all the blocks and check once again. If you have any doubts, let me know. Okay.
Where are
Share you again, or else any of you share output. Okay. So if you want to check more features like multiple slave, I mean multiple master, the clock address, clock stretching concept, trans 0116, and here write data will be um,
so
011100. This is one constraint.
so let's say we are not constraining
Mm,
the right address, read address, and write data.
mm.
So in the waveform, we'll be seeing all the combinations.
Yes, maximum all combinations we will check. Even here in .v file, here we have written as cases we will use two cases. Suppose 67 and 60 or else 57. And read address also 57, as it is a 1 bit size, it's a read operation. And here it's a DD. In place of DD, EE, suppose. Now you can check the output. What is the output here? Also correct. 57 FF and output write data FF and data out FF, both addresses 57. Here write enable is high, here write read operation is high. If it is high, write operation, if it is a 0, read operation. So this is how you can do the randomization also, even based on the constraint. Okay.
Verifying that particular feature, right? We are checking if the
Address,
applications should
destination address, SDA signal, and SCL signal. So SDA is low to high. Check here how both SDA and SCL are working here. Sometimes SDA is constantly high and low. The waveform, we should meet these requirements, the waveform requirements. SCL, however, it is changing here, and SDA. And another concept, arbitration. Arbitration, mostly if you want to design, we need to create master as a design, slave as a design, two masters, and through the arbitration you can connect. Or else um, suppose in single master, if we connect two test cases, then it will not work, because test cases is different and masters are different, both are different. So definitely we need to take two masters only. Or else, suppose if we create the same master as a test benches, two test benches, not test cases. So like that also we can create the arbitration, and if we trying to send the data from two, then we can use that concept. And also clock stretching concept. This just use this clock stretching example. Okay.
go in the waveforms.
Uh, you can check from your side if you don't get for clock. We shared the interview questions. Okay. Mostly these concepts only: arbitration, clock stretching, And if you put in your resume like you have developed some SV test benches and all, mostly those questions you will get. And pull up registers, pull down registers, registers we used right in the starting we discussed. So how we use those concepts mostly you will get.
What the
Pull up registers already discussed very clearly. I think you didn't join that session.
ma'am? No master is connect.
Transaction will be connected.
Okay. At idle, ma'am, the line is high or low?
Initial
When
case
not.
it will be initially it will be high only. We need to connect it as a low.
Okay.
Okay, any other doubts, others? WhatsApp also lock. Morning class will be there. For you, SV will be there. For SV.
Okay. Okay.
Evening session protocols at 7 o'clock. Saturday, what? Or else I will explain. Just download next.
Thank you, ma'am.